Okay, last time I introduced some notions from topology. And for smooth maps, we are very close to defining what a manifold is. But I want to define manifolds with boundary. So before doing that, let me because may found some kind of confusing if you see one definition but not the other. And okay, so we're continuing with smooth manifolds. So let's give some definition of a diffeomorphism. So let n be integer and u and v are subset of n. We say that u and v are diffeomorphic. This is a generalization of the topological notion of homomorphic. So homomorphism means continuous equivalence, and diffeomorphism means differential smooth equivalence. Diffeomorphic. If there exist smooth maps f from u to v and g from v to u that are mutually invertible, such that g composed with f is the identity of u and f composed with g is the identity of v. Okay. And we write u is isomorphic to v. Maybe, okay, well, this can be understood in many ways, the isomorphism symbol, but in this case, we mean diffeomorphic. So let's give some examples. So first of all, the most important case, which may sound a little bit strange, is that an open interval is diffeomorphic to the whole real line. So something that you think is small, in fact, is like the whole real line. So the first example is, let's fix, you see, if you have interval, you can stretch it a little bit, so it doesn't matter which are the endpoints. So let's fix from minus p over 2 to p over 2. I do this on purpose. So u is this and v is the real line. Can somebody think of a bijection, smooth bijection from this interval to the real numbers? I intentionally put minus p over 2 to pi over 2. Function that minus pi over 2 is minus infinity and plus pi over 2 is plus infinity. Yeah, tangent. So is smooth with inverse, of course, arc down. From R from V to U. Okay. So an open interval because we cannot jump to the endpoints in some sense. They're like some kind of infinity there, hidden. Second, generalization of one, any open brick so A1, B1 to A and Bn is diffeomorphic to R to the power n. So we just make tangent-like functions on each of the arguments and combine them. So if you have an open square or open cube, it's equivalent to the whole real line. Now let's make this halfway. For example, U is from 0 half open to P over 2, and V is R plus, so R bigger than equal or bigger than 0. So this is the set of real numbers that are, again, we have the tangent function here as well. So V is a diffeomorphism. And now if we generalize that, so this is generalization of 3. So if I have semi-closed only at one point, so a brick of type, so U is of 3 and also 2 as well. So not generalization, but uses 2. U is, let's say, here is half open, but from now on is open. And here to A and B. And now V is half space. So V is 0 to infinity times Rn minus 1. So this is half space. And so U and V are tangent-like components, let's say. Like component functions. Now let's draw this. So, for example, in n is the case n equals 2. We have, let's say, a square here that is closed only on this side, or a rectangle, doesn't matter. So this is A1, B1, A2, B2. So A1 can be achieved in some way. Not achieved, I don't know. So here we have closed, here on the other sides we have open, so this is U. And to infinity, this is V. So this is the half space where the x component is a non-negative. So this is 0 infinity times R. Okay. Now I'm doing that because when defining a manifold in boundary, authors usually parameterize with respect to this, but for us it will be more natural to parameterize with respect to this. Okay, so now we are going. Okay, so now we are going to define a manifold with boundary. I think. Yeah. So let m and n are integers, and m is a subset of R m plus n. So we say that M is a smooth manifold with boundary. I will omit the term with boundary because in our applications we usually work with manifolds with boundary. Where boundary conditions are imposed. So of dimension n, so smooth manifold on the dimension n, if for any point x in M, there are two possibilities. So first, one of the two following cases is true. No, the two. Cases is true. First, x is interior. So this is the case when x is interior point. So interior point has a neighborhood that is equivalent to an open space. So there exists an open neighborhood U. No, not U. Let's go with V. V. So of X. So that means that X is in V, which is subset of M. Such that, and smooth, bijective, and a neighborhood open neighborhood. Not my neighborhood, but okay. Not my neighborhood, but okay. U of Rn. This can be the whole space, it doesn't matter. Open set, open set, open set. U in so there is such a set, and a bijective immersion F from U to V. Immersion means that the differential of F has full rank. Has full rank. Here this means N. Here this means N. And the definition for boundary point is the same, just the space which, so this means that we parameterize V over U, I'll see in examples. And for the boundary point, this neighborhood is half space. So X is closed point, not closed boundary, sorry. I don't have space here, I'll write here. X is a boundary point. As a boundary point. So this means that there exists, this is case. So this means that there exists, this is case 2. There exists an open neighborhood V of X. Again, this means the same thing. And now it's this was open set. Now we have a half space and a bijective. Let's do a bit more general. And a set V in R n diffeomorphic to a half space, and a bijective immersion F from U to V. This is U not V, and a bijective immersion F from U to V. A very long definition, but the similar one and two are very similar, just the parameterizing space is different. Now let's give example of that. So the first of all, any open set in Rn is a manifold without boundary, is an n manifold, a smooth. So I have wrote of dimension n. Sometimes people say n manifold, smooth n manifold of dimension, any manifold without boundary. So when people say with boundary, this means it potentially has boundary. It can be without boundary. So all points are interior. Because we can take a bijective immersion. So for any x in M, we take, so for x set, let's say this is set M. For x in M, take U equals to V equals to M, and F is the identity map. So we take a point x in M and take neighborhood V of x. So we take the whole space, and we take U in Rn. So we say take the same space and take the identity map. So this is not interesting case. Let's give a bit more interesting case. Let's say B. I have only two dimension. N equals 2. And we take M to be BR of 0. So R is positive. Let's make it 1. B M equals B1 of 0. So this is the set of points such that x squared plus y squared is less than, so the closed ball, I take the closed ball, is less than or equal to 1. Okay, let's draw it. Here we have boundary. So M is a manifold with boundary. Two manifolds. What is the boundary of the disk of this? The boundary of this space. S1. Oh, this, okay. Yeah, this is the unit circle. No, this is the radius is 1. Yeah. So with boundary S1. So this is xy in r squared such that x squared plus y squared plus 1. Now let's see why. Okay, this is intuitive, but let's see why. So if x is interior, so if x squared plus y squared, let's call this point P. If P is interior, i.e. x squared plus y squared is 1, we can take parametrization by itself. We take a neighborhood, a small ball, let's say small ball V around P, and U equals to V and F is the identity. So again, if you are in interior point, it has small boundary that is equivalent to an open set because it's by definition to an open set because it's by definition is open this set U. Now let's take point in the boundary. So to point 1, let P is on the boundary, i.e. x squared plus y squared equals 1. For simplicity, I will take some point here. Doesn't matter because of symmetry. So for simplicity, let P is the point square root over 2 square root of over 2. So this is this point here. I don't know why I take no. Let be this point. So sorry. No, this will be a little bit hard for me. I will take P equals to 1, 0. I think it will be enough. So I have this point. And so I make some small circle around it. So let V is some circle with radius epsilon. Epsilon is small. Epsilon, for example, is small. Let's say 1/2 is enough. Doesn't matter. And now I get this thing here. Let me see if I can make it. So I need to find some set U that is isomorphic to this. I will fix this later. So let U be some space. I think it will be easier to make on the right, closed on the right, not on the left. And here the angles as well. I'm going to think about the angles also. And F from U to V is the following. So F is, let's go this R and let's go this phi, is oh no, this will be not enough. So I'm here in this space. You see, it has some boundary, but also interior. You know what? I should have made it differently. FRC. This is, if I make this thing here. R cosine phi, R sine phi. This will work. Over here. So R, if it's 1, okay. No, I just screw this up. This will not work that way. Okay. I'll make sure that on the right will be like no, this will not work that way. Okay, I will, no, not this way. I will, no, not this way. I will make it in a picture because I cannot think of formulas at the moment. So I'll take this point here, -1, 0, and draw pictures. So I'm here, and I'm taking some set like this. Things like that. And I'm mapping from a square. So I have this square, not square, a rectangle. And here I have fixed boundary. So this is V and this is U. And what I do is I make slices, vertical slices of this mapping here. Some way. So I need to map this to this maybe. Okay, I thought something completely different in my head, and I forgot to prepare formula for this one. But the idea is that around point on the boundary, you have when you make some cut, you have something like that. You have three sides that are open and one side that is closed, and it's like this half space. So this is, as I showed before, this is the same as a full half space, so things of that nature. This small rectangle, and I can map this to this, but this small rectangle, and I can map this to this, but
that is you. One.
Yes, yes, I agree. This is U, and the green is, the red is V, and this is F. It has to map in some way, but it has to be made rigorous because there is a counterexample that I will write now. Sorry about that, I completely screwed this up. For n bigger than 2, n bricks, closed n bricks are not smooth manifolds. People call them manifolds with corner. They're called. People call them manifolds with corner. They're called manifolds with corners. So if I have this thing here, the boundaries here, they are not smooth, the corners. Now, I think it's not that easy to prove that, but you cannot map this to an open disk, for example, or a closed disk, to closed disks. So if you want to map a disk to a square, you cannot make this smoothly. So if this is U and this is V, for example, so corners of a square or cube cannot be mapped smoothly, cannot be represented smoothly in some sense. And so when we're formulating problems on squares, cubes, something like that, we have to be careful to not do anything regarding derivatives on the corners. We can do derivatives everywhere else, but not on the corners. Example 4, so in general, let's generalize too. So for any n, B1, 0, for example. This is the set of points x1, xn in Rn such that x1 squared plus the closed ball. This is a smooth manifold with boundary. So disks, bricks are not smooth, but disks are smooth. It's a smooth manifold with boundary. And the boundary is the sphere with boundary and -1 sphere. Sphere. And so this leads to the definition, so the example of spheres. Is a smooth n manifold here. For any n bigger than 1, the n sphere and -1 sphere. So let's recall, this is the set of points in Rn whose sum of squares is 1. It's a manifold of dimension n minus 1. Is a smooth n minus 1 manifold without boundary, yes. So in general, case, let's make this as a theorem. It's easy to make a parameterize the circle. I mean, and the unit circle and the unit sphere, for example, I did last time. The polar and the spherical coordinates. Polar coordinates when the radius is 1, and spherical coordinates were local parameterizations of the sphere. Yes. So let n is integer and be a smooth n manifold with boundary. Let's say S. Then S is a smooth n minus 1 manifold without boundary. So this means that D of dm is 0, is the empty set. So the boundary of the boundary is the empty set. Manifold, sorry, without, I forgot to write without boundary. Without boundary. Yeah. Now let's go back to the sphere and the circle. They are interesting cases. I saw a set what are their parameterizations, but let's discuss it a little bit more. So note, I don't know. Consider the circle S1, M equals S1. Then if we take a point and let P is a point in this circle, then and for simplicity here I will make this working. For simplicity, assume that P is the point 1, 0. Okay, so here we are. This is P. And then take V to be any, like for example, the space cosine phi, sine phi, and phi is from minus, let's say, alpha to beta, where alpha and beta are positive, and beta minus alpha is, sorry, beta plus alpha is less than 2 pi. So I need to make some kind of, to take an arc, but it's not a full circle. So if this is, if the sum of this, so the length of the interval is beta plus alpha, and if it's at least 2 pi, it's a full circle. So I need to make it not full circle. Then if, and so this is an interval because 0 is always there, and so the point P is 0. So P is cosine 0 sine 0 is in V. And so V is a neighborhood, an open neighborhood of P in S1. So last time I spoke about relative topology. Open sets in the 2D space are like disks and unions of disks. But here, open sets are intersections of disks with the boundary. So if I take disk here and intersect it, I will get only part of the circle. Okay. So if we take U to be, let's say, the interval minus alpha beta, and F from U to V is obvious. So F of U to V is F of phi is cosine phi sine phi. Then F is bijection. F is a diffeomorphism. So F is a smooth bijective immersion. So let's compute the differential of F. It's bijective because we are not repeating any points. We are not making full circle. So F df is minus sine phi cosine phi, and it's never 0 because its length is 1. Its length is always 1, so it cannot be 0. And however, so note that V cannot be the full space, full circle. So we need, let's say, we need at least 2 parametrizations. And this makes sense of the term manifold. So it has many spaces in many faces in some way. At least in Bulgarian, it's like that. It has many images. So that's the difference between a parametrized surface, which has exactly 1 parametrization, and here we have at least 2. And so let me just conclude that with the definition of charts and atlas. So similar thing is true for the, if you remember last time when I spoke about the sphere, there were singularities around the meridian. That means that we cannot cover it with a single map. And I will make this now precise. So let M be a smooth and manifold. Here is cosine integer. Doesn't mean, it doesn't matter whether it's with boundary or not. A chart on M is a smooth. It's an it's an inverse of a parametrization. So it's an inverse of a parametrization. So it is i.e. it is a smooth map F from U to Rn from, let's say, from V, where smooth and with non-zero differential in some sense, but smooth and with non-zero differential in some sense, but so okay, so where U is open in M and V is diffeomorphic to Rn. So U is only interior, U is fully in the interior. Or to the half space 0 infinity times Rn minus 1. So U contains boundary points as well, contains part of the boundary. And also, let's say here is bijective. And F minus 1 is immersion, is an immersion. Or parametrization as well. And the map F is called local coordinates. And the map F is called local coordinates. And charts that fully cover, and a set of charts U, Y, F, Y for some set I in I. So I is an index set. It's called an atlas. It's called an atlas of M. So the idea is that, consider, for example, the circle. And we take two charts. We take, for example, chart like that. This is U1, and chart like that. This is U2. And they fully cover, when you combine U1 and U2, they fully cover the disk. And then you combine U1 and U2, they fully cover the disk. And they can intersect. And it's, in fact, it's beneficial to intersect. And the idea is that when you have a manifold, you cannot parameterize with a single map, but you can take parts, parameterize it by parts, and you have to have some kind of compatibility under common elements. But You're not going to do that. But a whole set of charts is called an atlas, and the idea, of course, comes from geography. When you have a chart, for example, you take countries and make charts of countries, but also a little bit take part of their neighbors. And now, when you have a full set of charts for all the countries, all the oceans, and like that, and all the continents, you get fully covered Earth, and any two charts that intersect, they intersect not only their boundary, but a little bit in their interiors as well. So if you take, for example, map of Germany and France, and then you take a little bit from the map of Germany to show the places in France near to the boundary, and vice versa. And now you have intersecting charts, and if you have a whole set of charts, you have an atlas. And the idea of local coordinates is that, for example, you have a point here. So let's say you can point here, x, y, and this is x is cosine phi. Let's take this point here, a positive point. This here. Y is sine phi. And this is a parametrization. However, if you want to go back, parametrization. However, if you want to go back from a point here to get a single number, this is a local coordinate. So phi is arctan of y over x. And this is local coordinate. And in differential geometry, when you have complex geometry, everything is done in local coordinates, and somehow you have to combine them globally. Okay, let's finish this lecture. Take a break.